That's what Gauss's law is about. It's about a relationship between charge and the creation of electric field. That's really what Gauss's law is about. And I don't see enough of you putting that someplace, so I'm going to say that again. Gauss is about the relationship between charge and electric field. It's not about flux. Flux is simply a way of measuring or encapsulating how much electric field there is. But Gauss's law says that the enclosed charge is equal to some constant times the total flux. So as an equation goes, it has power not in our ability to talk about flux, but in our ability to consider what it is telling us. So for example, I'm going to draw a picture here. These all represent point charges. All right? I want you to draw a Gaussian surface that would have 0 flux. If you're really paying attention, you'll know that there's several right answers here. And I want you to draw a Gaussian surface that would have 0 flux. If you can't read all these, this one's a charge of 2. Right here, let me get my pointer out. This one is a charge of 2. This one is a charge of -2. This one is a charge of 3. This is a charge of 3. And this is a charge of -1. So draw a surface that has 0 flux. Again, you're thinking of field lines, and look at what this says. Right here, the answer's there. If I want 0 flux, I need to enclose no charge. So I could have a surface like this one. That surface has 0 flux. It encloses no charge. Or I could have this one. Right? This one encloses 0 charge. The +2 and -2 cancel out. There's 0 flux passing through that surface. It doesn't say there's 0 electric field passing through that surface. The net total flux through that surface is 0, which means the amount of electric field that enters that surface is equal to the amount of electric field that exits that surface. So it's actually, there's a lot of different answers here, right? At least you probably can imagine there's a lot of different answers. I mean, I could pick, this one will not do it, but this one would. As long as I am enclosing 0 charge, I have 0 total flux. Write that in your notes. You won't remember. You think you will. Because it seems so simple. But I'll tell you what I'm going to show you on your test. There's going to be a picture of a bunch of charges and a bunch of different Gaussian surfaces. And it's going to ask which one has 0 flux. And you're going to be thinking, I have no idea. But it's that simple. Which one encloses 0 charge? That one has 0 flux. Move on or play around with this a little bit more? There's not a whole lot else I can do here, but you do realize now that we have that idea, if I just rewrite this, Q enclosed over epsilon naught, there could be any number assigned to how much flux there is. Let's stop for 1 minute though and talk units, just so that we have taken at least a moment to consider the units. If you remember how we calculated flux, it's an integral of E dot dA. But this is still just a product. By and large, it's still a product. Electric field is newtons per coulomb. Area is meters squared. So the unit of flux is Newton meter squared per Coulomb. We talked about epsilon naught yesterday. It's the permittivity constant, 8.85 times 10 to the negative 12th, and that's Coulomb squared per Newton meter squared. Put that in the denominator and you'll get the same units here. Now yesterday at the close of class I was trying to talk to you a little bit about the permittivity constant. And I need to explain to you something important about the permittivity constant, but it's not going to make a lot of sense to you. And part of that has to do with you get these constants thrown at you all the time. At least you do in physics. And when we start thinking about constants and simple ideas of Gauss's law, and name a constant that you've had to use in physics. I'm sorry, you're going to have to talk up. A spring constant. The problem with the spring constant is that there's a different one for every spring. So it's not considered a natural constant. Give me something that stays relatively the same, that doesn't change. Yes, sir? So when we talk about Earth's acceleration of gravity, we think 9.8 meters per second squared, right? But we learned more about this last year, maybe not much more. We learned that there's something called the gravitational constant, which is something that is the same everywhere in the universe and dictates how big gravity is. In my class last year, we only really talked about it a very little bit. But this is considered the universal gravitational constant. It is the same everywhere in the universe. We think that this gravitational constant can be used to make predictions about the way the universe works. 9.8 is meaningless outside the Earth. Right? It has no meaning outside the Earth. There are a group of constants that are considered to be universal in that they dictate the way in which the universe works. In this class, we will only really talk about two of them. And the first one is the permittivity constant. It's going to show up a lot. It's written like this when I write it, but as I always try to do with you guys, try to make sure you have an understanding of what it really looks like. So let's do my favorite thing and go back to kindergarten. So I'll need dotted lines there for the middle. So if this is a W and this is an E, epsilon is actually that size. It's lowercase. Okay? So when I write epsilon, I'm writing a lowercase figure. In type, it tends to look like that. I tend to write it as a kind of a semicircle with a little, or a C with like a little extension in there in the middle. The naught means free space. That's incredibly important since we never see free space or a vacuum. The permittivity of a vacuum is what that's signifying. That's what that little zero means. Because if you write just epsilon by itself, you're talking about the permittivity of some material. So there's the permittivity of air, the permittivity of wood, there's a permittivity of aluminum foil, there's a permittivity of styrofoam. Any material can have its own permittivity, but generally, the permittivity of free space is considered a constant everywhere in the universe, and that's the 8.85 times 10 to the negative 12th. And I want you to see this. It's Coulomb squared per Newton meter squared. Do you see how those units for the gravitational constant and the permittivity constant have some similarities? They both have this Newton meter squared portion. That's not accidental. It's because both of them determine the size of a naturally occurring force in the universe, which is why Newton is there. And the meter squared part signifies that whatever force that is has a meter square relationship. I don't know why the universe works this way, but both gravity and the electric force are proportional to the meter square. And nobody really can explain why. So there are other permittivities basically, in nature, we relate all permittivities to the permittivity of free space. We relate all permittivities to the permittivity of free space. We use this symbol, kappa, as a scalar to compare the permittivity of a substance to the permittivity of free space. And it's called the dielectric constant. Every material has its own dielectric constant. I am not going into it now, but we will talk about it a lot. Now, by the way, in about 6 months, you'll learn about the permeability constant. The permeability constant. It is kind of let's say the fraternal twin of the permittivity constant. The permeability constant is how well a magnetic field can be established in free space. It has an interesting consequence. These two constants can be independently measured. I mean, I can create an experiment to measure the permittivity constant, and I can create an experiment to measure the permeability constant, but together they predict the speed of light. And to get there is a long road, and we may or may not take that road this year, depending on how well you guys do, but there is something about the fabric of the universe here. And if you've been watching the news at all, the most amazing thing is gravity travels at the speed of light. No one ever thought to think that gravity had any speed at all, but we've begun to detect gravitational waves. And gravitational waves travel at the speed of light, which means that for whatever reason, these three things together predict the way the universe works, almost exclusively. There are other things related, but these three, for whatever reason, they tell us a lot about the way the universe works. So I never take minor the idea of a natural constant. Now, just so you guys are also aware, the numbers that are here don't mean anything. I want you to understand that they are proportionality constant to place our answers in the units that we earthlings choose to use. Somebody else, somewhere else measuring this probably measures a different number. They do so because they probably developed different units of measure. So these numbers are because we're in the metric system. There'd be a different set of numbers if we were in a different system. It's not the number that's important. It's the fact that there is this proportionality between charge and electric field. That's important. So, that's a lot. I want to talk about using Gauss's law now. And at this point, I'm going to give you a series of what I feel are ways to use Gauss's law. But I said yesterday, Gauss's law is all about symmetry. We can't use it without symmetry. So when we use Gauss's law, we're always trying to find some kind of symmetrical shape. So I talked to you about the infinite line of charge a couple days ago. And today I want to talk again about the infinite line of charge. And I want to see if we can't figure out what the electric field is around the infinite line of charge. It was an unsolvable problem for us the other day. You guys remember? So today, again, I want to give us the infinite line of charge. I want to have lambda represent the linear charge density of that line of charge. And instead of using Coulomb's law, we're going to add it all together. We're going to use Gauss's law. Now, Gauss's law has two parts. been trying to emphasize it, but there's two parts. There's the part about the charge, and there's the part about the field. The field part requires us to create a complete, bounded, closed surface. We can choose any surface we want. So I could truly wrap this in anything I'd like. That surface will still be able to tell me what the electric flux is and hopefully what the charge is. But sometimes there are better choices to make than others. So I want you to think about if we're trying to come up with a surface that might work. Let's take a moment and consider something that would be symmetrical, that would have a certain amount of useful, exploitable symmetry. To do that, I want to consider the line itself. Let's imagine, that's a little bit low for what I want to do. Let's imagine that this represents the line of charge as it's coming straight out of the board towards you. Is that okay with you guys? So this is still the line of charge. But we're now looking down its length. Do you not notice that if you look down its length, it automatically suggests a certain amount of symmetry? Meaning, if I was this far away right here, do you think that the electric field there would probably be the same size as the electric field there if I was X distance away? Like, doesn't the symmetry of the line suggest that there might be an electric field that streams outwards like that? So just on the onset, it would probably be nice if the surface I used could exploit that symmetry. Meaning I would like a surface where the boundaries of that surface are all the same distance away from the center. Now, this line I've drawn isn't great, but a surface that could do this when looking down its length. And I'm thinking of a cylinder, a can. Can you imagine a can? Because if I look at this angle, every contribution to the electric field would be the same distance away. I think I could use that symmetry for the outside edges of the can. Symmetry. Find the surface that you can use. I'm going to use this cylinder. Now, I need to kind of come up with some geometry for my cylinder. So I think you would all agree that a cylinder has height h, and it has a radius. I'm going to use lowercase r. Is that okay with you guys? I'll remind you, when it comes to flux, we calculate flux as E dot dA, and we have to make sure we use a closed bounded surface. But, and this is the best part about the fact that it's an integral, we're actually going to break this up into 3 integrals. Now remember what I said, our goal is to always make it so the electric field just pops out of these. It's our goal. So I'm looking at 3 different integrals. An integral that sums the top, an integral that sums the sides, and an integral that sums the bottom. Since it's a summation, all I had to do was make sure it took in all of the area. So if I do a sum of all of the top, all of the bottom, and all of the sides, it will be a sum of a bound and closed surface. Never said I had to integrate the whole surface directly. I can integrate them in pieces. Okay so far? Maybe? Here's the easy part. there is no flux through the top, so this is 0. Remember, the area is perpendicular to the field lines. No field lines pass through the top. That was the picture. That also means the bottom has no flux. The only thing that has flux passing through it is the sides. And when you remember that picture before, we have the line of charge. It would make perfect sense to ensure that my cylinder was concentric with the line of charge, so that this R is the same everywhere. Wouldn't that suggest that the electric field at all of these places would have to be the same size, because it's the same distance away from the line of charge? And the electric field is going this way, and the area is going this way. So wouldn't you see that the electric field and the area are both traveling in the same direction? I did all of that on purpose so that when I look at the exploitable symmetry, E is a constant, dA is just the area of the outer shell, and it will all be cosine of 0 degrees everywhere on the surface. And since the electric field is a constant everywhere on the surface, all I have to do is add up the total area of the outer edge of the cylinder. Which, by the way, you guys should know what it is. What's the area of the outside of a cylinder? Don't shake your head. I think you know the answer to this. If you were to unroll a cylinder, wouldn't it just be a rectangle? And wouldn't it be a rectangle that has a length of h and a width that is the circumference of the circle? I don't have to actually draw one and unroll it, right? You guys have enough of imagination to know that the area is going to be 2 pi r times h. Are you guys all okay with that? All right, well, that's a lot. Hit the high points. Find a surface with exploitable symmetry. Use that symmetry to try and identify areas that have no flux and areas where the electric field can be a constant. Done so. And finally, add up the total area. This represents the electric flux. That is this whole side of the equation minus the constant. So, I will write that out as epsilon naught times E times 2 pi RH. Now, all I need to figure out is how much charge is enclosed. And believe it or not, that's the easiest part of this. Density is charge per length. How much length of the line is inside the cylinder? H, right? That's how much is enclosed in my surface, which means Q enclosed is lambda times H. That's it. That's the answer. That's how you find the electric field. Now, this is kind of a mess. I assume you guys have stuff in your notes, so I can do this and come up with this all the time or at all. I am expecting that in March. Yeah, you can come up with it. My job now is to expose you to Gauss's law, both some of the harder stuff. But right now, we've used Gauss's law twice. Lambda H equals epsilon naught E times 2 pi RH. You see the H cancels, right? It's not accidental. Typically, the amount of charge inside will go away. You'll be left with a density. If I solve for E, I'm going to get lambda over 2 pi epsilon naught times R. Now, if you look back at your notes for when we did the infinite line, we had something that we were stuck. We had to integrate cosine squared of theta from negative pi over 2 to pi over 2. This might not have been an easier process, but it definitely gives us a simple answer, doesn't it? And look closely at this. I'm really trying to drive home this point. First, you can memorize this. This electric field for a line of charge. I would encourage you to consider it. There's only so many infinite shapes. And by the way, there's 2 infinite shapes. Line of charge, sheet of charge. If you remember, the electric field for a point charge is Q over 4 pi epsilon naught times R squared. Do you see the similarity here? Line of charge is proportional to just R. So the electric field coming off a line of charge is stronger. It should be stronger. It's spread out more. So it doesn't decay as fast, but it still does decay. Now, this was a lot. I can't minimize that. If you're getting 50% of this, you're doing great. This stuff is really tough. This process of getting here is so far beyond a lot of what you guys have learned so far in math and what we're doing in science. But I want to keep coming back to the results. I am not expecting that you... And in both sessions, we've come up with 2 conclusions. That a point charge gives us back Coulomb's law with a slight modification. Right, the modification is I'm no longer writing K. I'm writing a collection of constants that really are the underpinnings of what K is. And then I have the infinite line of charge. Now, I know you're saying to me, Mr. Shelton, what's the point? There are no infinite lines. But in real life, a long cable is an infinite line if you're close to it. I want you to think about that for a moment. Right now, there's a VGA cable that stretches from where my projector is all the way through the ceiling, all the way down the wall. If you're talking about the outer shielding of that cable, that's about 1 millimeter thick, but the cable is 30 feet long. To the shielding in the cable, it's an infinite line. We build things on purpose because they act like an infinite line when you're close to them. Why do you think the antenna on your car is a pole? It's a line of charge. And so we use the infinite line in the near field when we're close to something because it obeys many of the properties of the infinite line. When we do the infinite sheet tomorrow, that is every parallel plate capacitor on the planet is based on the idea of an infinite sheet. They're not infinite. They're just very close together for a sheet that is pretty small. So although these look like they're fake, they're really not. These are real things that exist in space. And this estimate is really close to the truth. And what I mean by that is, and you should follow along with this one instead of just looking at me glassy-eyed, if I have a line, and I say that the line is length L and total charge Q. On a problem, they might say you are close to a long line of charge. What is your electric field? They are not asking you to repeat the work here. They want you to recognize that the electric field at a distance z away would be 1 over 2 pi epsilon naught times Q over L times 1 over Z. They would expect you to be able to recall that. Or they'd expect you to do Gauss's law and then show this. They would not expect you to integrate it over the line. They would expect you to be smart enough to realize that if Z is small compared to L, that's an infinite line. That's what they want you to do. And that's why we study these using Gauss's law. Now, I'm going to go back to it, but just consider for a moment if I straightened out that line of charge so we could look at it from the outside, not in an isometric view. But doesn't it also look like the electric field would have to have this kind of uniformity to it? We kind of talked about that when we saw it before, and it'd be on the bottom too, in this direction. So I'm thinking, if I want to exploit the symmetry that I see here, I would like a surface that is equidistant from the line as I go around the line, but maybe a surface that has a top and bottom that are aligned with the electric field. So maybe a surface that could do this when looking at it from the side. And when I look at this vision of the can, I notice that the top and bottom would have no electric field passing through them. So they wouldn't contribute anything to the flux because the direction of the area is this way on the top and bottom. But the direction of the area is this way everywhere on the sides. Everybody following along with this? Because this is tough. This is as hard as it gets in here for the whole year. But this is what I mean when I say exploitable symmetry. Here, I chose a surface purposefully that didn't have flux.